We're going to now talk about the Simplex Tableau. So we're going to put in a more specific algorithmic framework the overall description of the conceptual simplex method that we discussed in the previous lecture. Again, our problem is standard form linear program, minimize C transpose X, AX equals BX non-negative. And the feasible set is entirely defined by the equality AX equals B. That's the information. Because in standard form, you know that you have X non-negative. And one simple observation is that AX equals B, this information is equivalent to a B inverse AX equals a B inverse B. I'm not saying anything. I'm just saying if you have equalities, you multiply by an invertible transformation, you haven't lost any information. Now, the reason that this is going to be useful for us is, again, by abusive notation. Let me write A as AB complement. Abusive notation because B is not going to be elements 1 through M. I'm just writing it this way. So in this case, AB inverse times AB is not nice now because I've got an identity, an M by M identity matrix sitting right here. So this is equal to identity and AB inverse times ABC. So before we even proceed, one immediate thing that we have here is that wherever that identity is sitting, that's telling us what the elements of B are. So this encodes the location of this identity, location of I, encodes B, what the subset B is. And now, what is this? Remember how we computed D. D, if we wanted to add a particular new element to the basis, I hat, we set D I hat equal to 1, and then the only thing that we needed to determine was the rest of the non-zero part of D, which we called DB. And what was that equal to? It was equal to AB inverse times that ith element of the I hat column of A. So in other words, what this encodes all possible DB vectors for any choice I hat that is not in the current basis. We're going to see how this is helpful. So now let's get to the basic Tableau. So the basic Tableau is essentially going to be it's going to explain an algorithmic approach for us to do all of the conceptual calculations that we have been talking about, and we'll do some examples. So XB is going to, this is the Tableau, the basic Tableau is M by N plus 1. N is the number of columns of the matrix, and I've added one column here. So this is XB, of course, is AB inverse times B. And then in here sits AB inverse times A, which, as we said, has two parts. So let me erase this and write the two parts of it, which are the identity and AB inverse AB complement. And just what we had on the previous slide. But now I'm writing it in a box. So again, this is B. This is B complement. And remember that this encodes all values of DB, which was equal to AB inverse A I hat, where I hat was not in B. And what did we do? We're going to choose some I hat that is not in B. We know we're going to choose it so that it has a negative reduced cost. We'll get to that in a minute. And but I want to map everything we discussed in the previous lecture to this Tableau. So we choose some I hat not in B. So what's I hat? It's some element here. We're going to do an example in the next slide, but just setting up the conceptual framework here. And then what's theta? We choose theta, we said, as the ratio with the elements of xb. So remember that this was equal to the min over all j such that dj is positive, j is an element of b, xj divided by dj. And the winner here, let's call that j hat, this exits the basis. And our new basis is b minus j hat union I hat. Now, how does this work in the context of the Tableau? So we're going to look at the I hat column. And what is the update? Remember, x new is equal to x plus theta d. And db is equal to minus a b inverse times a I hat. So we are looking at positive elements here and comparing them, looking at the ratio to the elements of xb, because when you move 1 unit in the db direction, this element here decreases by theta times this element there. So we're looking at this ratio. So this is how we determine it. It's going to be best to just describe this, to do a specific example so that you can see how the numbers work. So let's go through this. So my example is 3x1. I have 5 variables plus 2x2 plus x3 equals 1. I'm just going to write out the 3 equality constraints. 5x1 plus x2 plus x3 plus x5 is equal to 3. And 2x1 plus 5x2 plus x3, whoops, this should be an x4 here, plus x5 is equal to 4. Okay, so this is my vector b, and the coefficients here are my vector a. So let's quickly write down the information as b a. Okay, so I've got 1, 3, 4. This is my b vector. And now I'm going to write my a vector. So it is 3, 5, 2 is the first column. 3, 5, 2. 2, 1, 5. 1, 1, 1. 0, 1, 0. 1 because I had this x4 here. And 0, 0, 1. That 1 is that x5. So here is a summary in a Tableau form. Now note that I don't know what the basis is yet, but I see that at least in this example, if I subtract the third column, so the third row from the second row, and the third row from the I'm pointing to the right thing and saying the wrong thing. If we subtract the first row from the second and third rows, then we're going to have an identity sitting in here. So if I subtract 1 times row 1 from row 2 and row 3, what have I done? This is a row operation, And we know that all row-column operations are invertible. And remember that I started out this discussion with the obvious observation that if I have a set of equalities, AX equals B, if I multiply the set of equalities with any invertible matrix, I've preserved all the information. And so if I tell you that AX equals B, or T times AX equals T times B, where T is some invertible m by m matrix, I haven't changed anything. And all row-column operations are invertible. That's why when you first took a linear algebra course, you learned how to do things like put something in upper triangular form or diagonal form or whatever using these row-column operations. And in fact, that's how you first learned to solve linear equations, probably. So these are all invertible. So if I do this, I move to the Tableau. Bear with me. I'll write it out quickly. You can verify the math later. Well, let's just check. I subtract the first row from the second row, and therefore the 3 becomes a 2, the 4 becomes a 3. The first row is going to stay the same. 3, 2, 1, 0, 0. The second row is going to become 5 minus 3 is 2, etc. Minus 1, 3, 0, 0, 1, 0, 0, 1. Aha! We have an identity here. So it must be. So now we are sitting at an extreme point. This is the only conceptual leap. It's not really a big one, and we're just kind of moving quickly here. What have we done? I'm saying that my basis is 3, 4, 5. This is A, B inverse times A, B complement. And this is A, B inverse times B. So that means that the point, let's write it out, the point 0, 0, 1, 2, 3 is an extreme point. Let me use this notation, is a basic feasible solution. Okay, so we're now starting at a basic feasible solution. Why did I put 0, 0, 1, 2, 3? Because x, remember, x has the form xb 0. What's xb? It's 1, 2, 3. What are the indices of b? 3, 4, 5. So I put 1, 2, 3 right there. This is my xb. And xb complement must be 0. Everything in there is 0. Okay, so here we are. I've started this. Let me copy this. And let's continue on with this example. And let's introduce a new element in the basis. So what are our choices? Our choices are something that's not in the basis. I have to choose some element from B complement. So let's just choose, again, the proper way to do the choice, which is coming next, is to be keeping track of the reduced costs. We're not doing that for now. Let's choose I hat is equal to 1, just to get used to the mechanics of Simplex method. So what does that mean? That means that I'm going to introduce this element into the basis. Currently, only elements 3, 4, 5 are in the basis. B is 3, 4, 5. Okay, so what does it mean to, remember now, what is this column here? This column is equal to A, B inverse times A1. That means that x new is equal to my old x plus theta times my d new, the d. What is d? I put a 1 in the I hat location, a 0 everywhere that's not b or I hat. In this case, there's only one such index, that's 2. And here I put AB inverse db. I'm sorry, minus that. And so I have here minus 3, minus 2, plus 1. And I choose theta to be as big as possible while making sure, let me write out what x is a little more carefully. All right, so x is 0, 0, 1, 2, 3. So what's going to happen as theta grows? Which one of these is going to hit 0 first? But you can see this element, the fifth element, will never hit 0. Theta is positive. And it's really going to be, it's going to be this element. So how big is theta? Theta is the min over all positive values here of it's 3 divided by 1 and 2 divided by, sorry, it's x over j. It's x over j because that's how big theta can be. I need to divide by x. So it is 1 divided by 3 and 2 divided by 2. So this is the winner. So that means that j hat, the element that exits the basis, is this one. That's not element 1. Remember, this value here is the first element of the basis. That's element 3. So j hat is equal to 3. So this is called the pivot element. Let's write this down again, just kind of cleaning it up a little bit. So here's my Tableau. We're going to introduce this column. This is I hat. 3 is the pivot element. It's called the pivot element. And j hat, which is index 3, it's not 3 because the circled thing is 3. It's 3 because it corresponds to the first element of the basis, which is 3, 4, 5, is the basic variable that exits. So my new basis is equal to 1. 2 was never going to be in it. 3 used to be in it but exited. And 4 and 5 remain in it. And now, what do I need to do? I need to do basic row-column operations so that this column now must look like 1, 0, 0. And what are row-column I'm only really doing row operations. I'm allowed to divide the row and multiply the row. So I can multiply it by any non-zero constant, and then I can add multiples of the row. So we can see what's going to happen here. In order to make it look 1, 0, 0, I need to divide by 3 and then subtract it from the second row and add it to the third row. And so I must divide first row by 3, which is my pivot element, and subtract it times 2 from the second row, and then add it to the third row. How am I getting this? I want that column to look like 1, 0, 0. And once I do that, what results, you can check the algebra yourself, is 1/3, 4/3, 10/3, 1, 0, 0, 2/3, minus 7/3, 11/3, 1/3, minus 2/3, 1/3, 0, 1, 0, 0, 0, 1. What do we have? We know what the basis is. It's equal to 1, 4, 5. And we know what xb is. It's equal to, it's equal to first element is in the basis, so I look at my table, it's 1/3. The second element and the third element are not in the basis, so I know it's 0, 0. The fourth element is in the basis, so I look at that first column, it's 4/3. And the last element is again in the basis, so it is 10/3. You can check all of this. And this is now how we would proceed. So this is how all of that information in the conceptual simplex algorithm is encoded into this Tableau. Now let's talk about the reduced costs. So remember that C bar is equal to C minus CB transpose A B inverse times A. This is so important that I'm going to start giving it its own name, P. So I'm going to write C bar is equal to C minus P transpose A, where P is equal to CB transpose AB inverse. And recall that if I is in B, then C bar I is equal to 0. And if C bar is greater than or equal to 0, then my basis and the resulting solution, XB and 0, is an optimal solution. We're going to talk about how we can now incorporate these into the Tableau with the same type of row-column operations. So I'm going to add a 0th row to the Tableau. And my 0th row is going to look, so my Tableau is now going to look like this. It's going to be, I'm going to have m plus 1 rows and n plus 1 columns. And up top, I'm going to keep C minus CB AB inverse times A. As always, I have A B inverse times A here. I have A B inverse times B here. And then here, I'm going to put, it makes the algebra work out, the negative of C transpose X. So what goes here is negative C transpose X, which is equal to minus CB transpose AB inverse B. And remember that this is equal to identity and AB inverse AB complement. So what we learned so far is that the update rule, we don't have to keep inverting AB inverse. We have a very efficient way to do this just by row column operations. So what we learned so far is that you want to introduce I hat into the basis. You look at that column, you find out the pivot element by looking at the ratios with AB inverse B, which is sitting in the first column of the Tableau. You find which is the minimum. That's your pivot element. You divide that row by the value of the pivot element to make it 1, and then you just add it to the different rows in order to make that column that you introduced to look like, to look like, if the pivot element was, say, second out of 5 potential rows, you'd want that pivot column, that column that you introduced to look like 0, 1, 0, 0, 0. It's got to take its place in the identity matrix. Okay, so what about, and we also saw that this automatically updates AB inverse B, basically for free. It's the same type of things. So now we need to understand how are we going to update this 0th row. And it turns out that we're going to update it in a very, very similar and simple way. What do we need? Okay, so my main question is how to update this 0th row. And let's think about what must it satisfy. what is sitting up here? It's the reduced costs. And what do we know about the reduced costs? We know that CI bar equals 0 for I in the basis. So in particular, we need to make CI hat bar equal to 0. It wasn't 0 before. It was strictly negative. That's why we introduced it into the basis. That's why we're going to use the I hat reduced cost to make our choice that we're going to now add the I hat column. Right? And so what we need to do is now make, in the new basis, we need to make sure that that is now 0. We know if we just computed, if we found the new basis using all the techniques we did before, computed the inverse of A, etc., this would work. But we would like to do that. We'd like to do that more efficiently. So the claim is that this will automatically happen by row-column operations if we make CI hat bar equal to 0. How do we do that? Again, by the only thing that we're allowed to do, add multiples of the pivot row. The same thing we use to make that column be an element of be one of the columns of the identity. We're going to add or subtract a multiple of that row with the pivot element. The pivot element was 3 in our previous example here. Right? When we divide by 3, this looks like 1, 2/3, 1/3, 0, 0. We're going to add or subtract that to the 0th row in order to make the ith element of the 0th row equal to 0. So by adding a multiple of the pivot row. So if we make CI hat equal to 0 by adding multiple of the pivot row, then the 0th row becomes our 0th row here has the cost CB new times AB new inverse times B, and the updated reduced cost C minus CB new times AB new inverse times A. So basically I'm saying that this operation is going to give us what we need. So this was so we need to show this claim. This was actually what I was going to write on this slide here. But let's let's show that this is let's prove this claim. So what do we start with? We start our 0th row initially has the form 0C minus CB transpose AB inverse times BA. So I've broken down this first row. So again, what is the first element of the first row? It's minus CB AB inverse B. That's what's the first element of the first row. So this is why I'm writing it in this way. And we're going to add a multiple of the pivot row. What's a pivot row? It's basically row J hat corresponding to the exiting basis variable. So what is this jth row? What does the jth row of the Tableau look like? flipping back so you can see exactly what I'm talking about, I'm saying what does this, let's look at what this row looks like. This is what I'm going to be subtracting from the objective. Sorry, from the zeroth row. Well, it has zeros in the elements that are not exiting the basis. So it will not change those values of the reduced cost. That's good. That means that those will remain 0. It will change the reduced cost of the element that stays. The element that leaves. And how is it going to change it? Well, this element, because we introduced it, was negative. So we're going to be adding positive multiple of this row to the 0th row. That means that this is going to become 0 and this is going to be positive. So that's good. That's going to tell us that we're not going to immediately want to put that element back in the basis. This means that we're making progress. But the main point is that what does it look like? It's going to be this update, this jth row that we're adding looks like some multiple of B and A. Where what is H? H is the corresponding row of A, B inverse in our calculations. So what's happening is so that means that once I look at this update, once I add this to this row, what do I get? I get 0C minus CB A B inverse. Sorry, let me take away this transpose and put it outside. Plus, actually no, we need it there. Plus alpha, some multiple of that row H, times again BA. And I'm going to call this my updated P. So what is P? Do we have enough to determine it? How can we compute P? Well, first of all, so what do we know about P? What is P? I know the following. We know that alpha is chosen to make Ci hat bar equal to 0. It wasn't 0 before. So we have one equation for P. We know Ci hat bar equals Ci hat minus P transpose AI hat. This is equal to 0. This is our choice of alpha. But we also saw from the example here that all the other elements of the basis, except for the element j hat that exited, remain at 0. So we also have that Cj minus P transpose Aj equals 0 for every j that's an element of B, except for that j hat that exited the basis. So what does that mean? That means that Ci minus P transpose AI equals 0 for any I that's in our original basis minus j hat union I hat, which is just known as our new basis. Which basically tells us that P, if you write out all these equations, it tells us that C B new minus P transpose A B new is equal to 0, or that P has exactly the right form. What was P? What do we want P to be? We want it to be this, but with a new basis, and that's exactly what we have. P is equal to CB new transpose A B new inverse. So there is a lot of notation that we've gone through here, but step by step, it's very straightforward. So please look through that to make sure that that you feel good about what's happened and understand the basics of the simplex method. The overall point is that our simplex method looks like this. Up top we have C minus CB transpose A B inverse A. Here we have A B inverse times A. We've got here A B inverse times B, and here we have minus C B transpose times A B inverse B. And the way that simplex works is step one, we choose I hat such that its reduced cost is negative. Then we find the pivot element. Okay, so let's suppose this was our choice for I hat. Then we're going to find, by looking at a ratio of elements of this column with elements of this column, we find the pivot element. Once we find the pivot element, we add multiples of the pivot row. This is now my pivot row, to make the pivot column look like what? It needs to have up top a 0, because that's the new reduced cost, and it has to have zeros everywhere else except for a 1 in that spot. It becomes this vector becomes an element of the identity matrix. So this is a summary of the simplex method. The point is that all of these inverse operations are basically done nearly as efficiently as possible, but also it very compactly represents everything we need. Next, we're going to talk about duality, and we'll see how the simplex method not only encodes the primal solution that we have so far, because this is xb, but it also encodes the dual solution. And we're going to see that the dual solution is going to be sitting right up top here. And that's why we've been making a big deal of that and giving it its own name. But we're going to pick that up next.